In the past few lessons, we've been talking about how to verify the integrity of our data. We started out with parity, and parity was a single bit, which, well, it told us whether or not we had an odd number. Well, told us. It made sure it verified. It was a single bit that was added to the end of our data that verified an odd or an even number of ones in the data. So for example, if I had 5 ones in a byte and I needed to have even parity, another bit was required in order to make it so I had an even number of bits. Parity was great in a number of fashions, except for the fact that if I had a single parity bit, it could only tell if I had an odd number of bit flips. So we kind of made a little bit more robust error checking tool in a checksum. And a checksum, a basic checksum that was based on a datasum. So we were able to take all of our data, and maybe we're sending bytes of data, and we would add all the bytes together and take any carries that came out of that byte and put them back in. And the final value, the final sum, the datasum, could be used to also check or verify the integrity of our data. And that actually works very, very well. But there actually is a drawback. Remember, we tried to transmit the letters HELLO exclamation point, the ASCII values, 8 bits, so every single one of those started with a 0 because those letters are all able to be represented in 7-bit ASCII. And so what we had was the H, which was 48, and then we had the E, which was 65 hex, and then the 2 L's, which were 6C apiece, and then 6F for the O, and then the exclamation point was 21. And whenever we added these together to get the data sum, remember what we're looking at is, once again, we're adding each one of these bytes together, and any carries that came out of the most significant bit get added back in. And our final result, our data sum, was 17 hex. All right? And so, what is the problem with this? Well, let's convert these to binary real quick. All right, so there's our sum. And so when we add these all together, and like I said, if any carry comes out of the most significant column, then we simply add it back in. What happens if I get a bit flip? Well, let's flip one of these bits. If I flip that to a 1, well, that's going to change and modify our result. So we have a slightly different value. The problem is in that same bit position, we have 4 other values that also have 1s in that position. So what if, we had a 0 change to a 1? What if we have a 1 change to a 0? Guess what? We had an equal and opposite equal in magnitude and opposite in direction change to our data sum, and guess what? The data sum would be fine. Another way of looking at this is to take a look at a number line. If I have a number line, and let's say at this point this is our goal for our data sum, then what happens if I get a bit flip? Well, any bit flip could be in either a positive or a negative value. So a bit flip from a 0 to a 1 would add to our data sum. A bit flip from a 1 to a 0 would take away from our data sum, right? Well, every single one of those adding or taking away is going to be a power of 2. For example, this one right here, and going from a 0 to a 1, it took our data sum and it added 4 to it. In the other direction, though, whenever I change this from a 1 to a 0, whenever that bit flips, it just happened to be in the same column, and it happened to be in the opposite direction. Whenever I went from a 1 to a 0, I took away 4. And so since any error in our data, there's really only, if I'm doing 8 bits here, there's really only 16 possible errors that I can have. I can either add one of my 8 powers of 2, or take away one of my 8 powers of 2. So there is a little bit of a problem with checksums. They are still used greatly. They're used all over the place, but there's actually a more robust form of error checking. Let's check it out. Now, instead of looking at our data as individual bytes, let's just put everything together, one long serial stream of all of our data. Let's do this. We have our capital H, which was a 4-8. And then we had our lowercase e, which was 6, 5. Right? And then we had our two capital lowercase l's, which were 6c. All right. And then we had our little o, which was 6f. And then our exclamation point, hopefully I have enough room for this, which was 2, 1. All right. Now, if I look at this as one long number, any of those bits could change. But what happens is if a bit changes over here, it has a very large effect, right? A great deal of effect in the magnitude, the overall magnitude of this long 48-bit number. And as you go through this from left to right, the changes have varying effects. So we have small effects over here and incredibly large effects over here. What we really need is the ability to, well, come up with some sort of a hash. Remember, I don't know if you have a lot of experience with computer science, or computing in general, you've probably experienced this idea or encountered this idea of a hash. Now, what a hash does is it takes a very large number and it, well, seemingly randomly assigns it to one of like a certain number of buckets, so to speak. A good way of doing this is, for example, if I've got these very long IDs and I have a limited number of memory spaces where I might classify one of those IDs, well, I can take that large ID and distill it down into a seemingly random value that will just kind of randomly pick or hash into one of those locations. A very common way of using this, or a very common implementation of the hash algorithm, is the modulo function, the mod function, where we figure out the remainder after dividing it by some sort of an integer. Well, if we looked at this as a very large number and applied the mod function to it, in fact, let's go ahead and try this. I have figured out that this value right here is equal to, as an integer, if I were looking at this as an unsigned integer, as 79600,447. Yes, I'm copying this down. 942,433. All right, I think I got that right. That large integer. So this unsigned binary value is equal to that large integer. What if I were to do the mod or the remainder function for something like mod, I don't know, how about 147? So this number, mod 147, what is our value going to be? Well, we know right up front that if I'm going to be dividing this number by this and looking for the remainder, then I have 147 possible results. So what I'm doing is I'm taking this large number and I'm basically classifying it into one of 147 different places, going from 0 all the way up to 146. So that's our range. Well, it turns out that whenever you do perform the modulo of this number with 147, the result is 131, all right? Now, something to look at real quick is that's not a power of 2, that's not, I mean, it's kind of just a seemingly random value. Now, what if I made that change like I had done earlier, where I flipped this bit to a 1, and then the corresponding bit in the E, the corresponding position in E, I flipped to a 0. What is that value now? Well, it turns out that this new value, this modified value, this value that is an error, is 83,981,314,584,353. All right. And notice that we actually had a significant, I mean, that change right there did do a significant change to our magnitude of our unsigned 48-bit integer up here. But what did it do to the modulo? So if I do mod 147 again, what I get is 74. Now, this is just kind of a random jump. And what's really nice about this is that the bits changing, as you change the bits in the different positions, they will have a very different effect on this resulting modulo output. So, can we do this in the computer? Can we treat a received block of data and just simply perform the mod function on it? What is the mod function? Well, you got to do a division, right? There's a couple of ways. I mean, the most basic way is I could repeatedly subtract 147 from this number, just over and over and over again. Keep repeating until the result is less than 147. That's our remainder, right? That'd take a long time. That would take a very long time. And there's another problem with that. The second problem is I'd need to have the whole value. I'd have to have the whole result before I could do the operation, the algorithm. So I'd have to receive all 48 bits before I could start doing that. I couldn't do any sort of processing as the data is coming in. Turns out there's a third problem. 48 bits. Sure, we've got 64-bit processors, 128-bit processors. Shouldn't be a problem. But how many times are we actually only going to send 48 bits? More than likely, we're going to send something like 8,000 bits. How many processors do you know with an 8,000-bit register? Specifically, an 8,000-bit register that's capable of subtraction. Ain't any out there. So, are capable of repeated subtraction for all those 8,000 bits. So, Tarnoff, you have just told us that the mod function is a great way to do error checking, and now you tell us we can't do it. So what's the use? I'll tell you what the use is. The reason why you need to do, and in fact, let's just talk about long division. Let's do long division. Let's do 5 divided into 239, all right? So we're doing our long division here. What do you do? Well, when I look at this value that I'm dividing 5 into, I first start at the first digit. And if the first digit is smaller than the value I'm dividing into it, I grab another digit. And in fact, I keep grabbing additional digits until I've got something that I can divide 5 into. Well, 5 doesn't divide into 2, so I grab the next digit, 3, right? So 23. Yeah, 5 does go into 23. It goes into 23 4 times, right? So we take 20 out, we're left with a remainder of 3. And that's when I drop the 9 down, right? And so now 39 divided by 5, well, it can go in 7 times. That gives us 35 with a remainder of 4. So the mod function, as we're looking at it, is this that 5 divided into 239. We got the modulo of 239 mod 5 is 4, all right? How can we do this here? I mean, this sort of kind of looks like the idea that I could do long division, but the problem with this is the borrows. What makes it difficult to implement this digitally and to make it slower and to make it so that there are changes, any sort of a change in, for example, if I've got something a bit that flips down here, like this 0 turns into a 1, it suddenly has to borrow from possibly far up the chain. So there's a lot of interaction of the bits left and right across our number. What if, instead of using borrows, we did, well, I'm going to make up a word here, a borrowless subtraction. By doing a borrowless subtraction, then what I could do is that same process, the long division, except instead what I do is I just simply ignore the left to right interaction between the bits. So let me do an example here real quick. Let's just do, how about 1 0 1 1 0 1 0 0. And we'll do a subtraction of 1 1 1 0 1 0 1 1. All right. Actually, let's just change one of those bits to a 0 just to make it so that we've got every option here. Now, what you're looking at here is, well, in fact, this subtraction should result in a negative number, right? The bottom number in unsigned binary is larger than the top number. But with this borrowless subtraction, the overall magnitude, the relative magnitude doesn't matter. What matters is that the two most significant bits are both ones. I'll explain why that is in a minute. Now, to do a borrowless subtraction, if I try to take 1 out of 0, I need to do a borrow. Don't perform the borrow, but assume the borrow has occurred. So if I were to take 1 out of 0, well, 1 out of 2 would be 1. And so once again, assume the borrow has happened, but don't actually perform it. 0 minus 1 is 1. 1 minus 0, of course, is 1. 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0. 0 minus 1 is 1. And 1 minus 1 is 0. All right? Now, this might look a little familiar. Turns out that, well, if the bits are different, the result is 1. If the bits are the same, the result is 0. That sounds like a bitwise exclusive OR. And in fact, that's exactly what it is. It's a bitwise exclusive OR. Now, this bitwise exclusive OR, the reason why I wanted to make sure that these most significant bits are both equal to 1 is that we are looking to make it so that whenever you do this subtraction, that this most significant bit, and possibly bits to the right of it, are all 0. Because what you're looking to do, like with the subtraction with the long division in decimal, what we're looking to do is make a result we're looking to take out of or remove from the number we're dividing into with the number we're dividing by. And so these two values must both have 1s in the most significant position. Now, another thing about long division in binary is that it's either going to be one of these taken out of the value we're dividing into, or 0 of these taken out of the number we're dividing into. So what's going to happen is we are going to progress like we would with long division through the number, subtracting the value we're dividing by. And that's really the operation that we're doing here. So let's go ahead and do a little bit of that operation right now. Now, we go back to what our original discussion was, because what we're looking for is error checking in a long stream of bits coming in across like a line of communication. So I've got this long stream of bits that make up a large amount of data. And in fact, let me go ahead and put these guys back the way they were so that I can, well, clean up the board a little bit. So this was a 0. And that was a 1. All right, so these bits are coming in, and what I want to do is act like we're doing long division. Now, something that may not make sense right now is you're going, well, you've completely screwed up the operation of the mod function. The result we're going to get is going to be wrong. It's not going to be mod 147 or whatever it is. Turns out it doesn't really matter. What we need to do is simulate it, because it wasn't necessarily the number that we were looking at. It was the activity or the result of taking a large number and hashing it into one of those values. And so what's going to happen, let's just do it this way. As the number is coming in, and let's just say that I've got this divisor, and I'm going to use, I don't know, how about 1001 0011. This is in hexadecimal a 9-3. It just so happens to be equal to 147, which was what we were using before as our divisor. So 9-3 hex. Now, this number is coming in, and what we're doing is we're receiving bits. Now, as we receive the bits, what we need to do is wait until this most significant one is in the 8th bit position, so it lines up with the most significant one of our divisor. As I get these bits in, if I get to this point where I've got the first 8 bits, and you think, well, 8 bits, I've got 8 bits in our divisor. No, remember, the most significant one of this divisor has to line up with the most significant one of the value we're going to do this bitwise exclusive OR with. forth. So I keep receiving bits, and I'm going to receive bits all the way up into this point right here. Now that I've got 8 bits with the most significant bit being a 1, I can take my divisor 1001 0011, and I can do my bitwise exclusive OR with that. By doing the bitwise exclusive OR with that, now I've got, we can start on the left side here. So 1 exclusive ORed with 1 is 0. So we've got same, 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 same. Wow, this is pretty close. And then we got 0 exclusive ORed with 1. That's a 1. 0 exclusive ORed with 1. That's a 1. All right, so we store those bits. Those bits are going to be stored, and as we're storing them, but we keep or maintain what's called a shift register, where not only are we taking as these bits are being brought in, we're storing them to memory, we're also taking these bits and putting them in and shifting them into the shift register that is the width of our divisor, and waiting for that 1, the most significant 1 in that shift register, to be the most significant bit. So these bits keep coming in. So I'm storing this data, and along with storing this data, I'm also bringing in these bits, right? Now, I keep bringing in these bits, and so I've got 1, 2, 3, 4, 5, 6, 7. Need to bring in that 0. So now I have 8 bits with the most significant 1, right? That 1, and these bits are being stored also in memory in case the message is okay. Now that I have 8 bits here, I'm going to bitwise exclusive OR it with my divisor. So I'm going to do another bitwise exclusive OR. We've got the same 0, different 1, different 1, same 0, same 0, same 0, same 0, different 1, okay? So now this is what's in that shift register. So I keep bringing in bits. The next bit that comes in is a 1. I add it to my shift register in addition to storing the data. I've got 8 bits again. I do a bitwise exclusive OR with my divisor. So a bitwise exclusive OR 10010011. This is same 0. Notice how every time I do these bitwise exclusive OR, the most significant bit of the result is a 0. So I've got 1 exclusive ORed with 1 is a 0. Then we've got different is a 1, same, different, same, 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 same. All right? Keep bringing in the data. And the next bit that comes in is this 0 right here, I hope. That 0 right there drops down there. Now I've got 8 significant bits. I've got my equals my divisor. So I do 1001, 0011. I do a bitwise exclusive OR, same, same, different, different, same, same, different, different. All right? And you get an idea of the process. Now, there's a couple of things to note here. The very first thing is that as the data is coming in and being stored, I don't need to wait for the whole number to come in before I can perform this operation. The operation can be done as the bits are coming in, as long as I just simply make a copy of the bit that's received. After I've stored it, make a copy to push it into this shift register and wait for me to get 8 significant bits. Once I get 8 significant bits, do a bitwise exclusive OR. Forgot to put my circle around that one. Do my bitwise exclusive OR with the divisor, get the result, and keep shifting in the bits. By the time I get to the end, then what I have is a pseudo mod function or a pseudo mod result. And it's just as effective as a regular long division, except we've solved the problem with needing to get the whole number into a single register, and we've also solved the problem with the time it takes. There you go. So this sounds like a way to solve our problems. And in fact, it is. It is something called a cyclic redundancy check, or a CRC. And it's used in a lot of communication methods. If you look at Ethernet, Ethernet has a divisor, and by the way, they're not called divisors. They're actually called polynomials. All right, so there is a polynomial that every Ethernet card uses to do its CRC. It uses a 33-bit polynomial, and, well, 33-bit seems like a really weird number, doesn't it? Yeah, let's take a look at our results over here. Whenever I did each one of these bitwise exclusive ORs, remember that the most significant bit, the one that was here and the one that was here, always resulted in a 0. What is the largest value that our mod result is going to be, or our pseudo mod result is going to be, if I have an 8-bit polynomial? Well, if I have an 8-bit polynomial, the biggest result I'm ever going to have is 7 bits. Because remember, the ones in the most significant bit always cancel out, so the highest result I can have for this remainder is going to be 7 bits. That means by using a 33-bit polynomial for our Ethernet cyclic redundancy check, a 33-bit is going to result in a CRC, and they're called checksums also. They're going to result in a CRC checksum of 32 bits, all right? So we put this 32-bit CRC at the end of all of our data, and as that data is being received by the Ethernet card, it will do this exclusive OR with the same value that every Ethernet card shares, and it will keep doing it, and it should, by the time it reaches the end, have that CRC. There's a really unique thing, though, that's happening here. That last value, that last mod, that is really kind of the remainder, right? Well, if you actually keep bringing that in and do one last bitwise exclusive OR with the remainder, guess what the result should be? Should be 0. That's a little bit of an idea, or just a little bit of a taste of what it's like to do a more robust error checking using this idea of a mod hashing using borrowless subtracts in order to determine if we've got any errors in our data.